Hello, everyone. My name's Lucas. I'm one of the co-founders at Centrifuge. I'll be talking a little bit about how we can use off-chain assets in DeFi, how we mint NFTs using snarks. We'll be packing a lot of theory and exotic topics into the talk, so it'll be the very high level. But the good thing is there are two very comprehensive blog posts you can read about if you want to dive into detail, or just hopefully we'll have a bit of time for questions afterwards. But before we start with all that, a little bit about Centrifuge, and I'll start with our mission. Our mission is to change the rules of global trade to foster economic opportunity everywhere. What this means, I'll show you in an example of how we're working to enable businesses to access funding more easily for growing their business, for sort of doing the things they do today with in the traditional financial ecosystem in this new world that we're trying to build together here. To start with that, I'll give a very brief introduction of the Centrifuge core protocol, and then sort of add layers and layers of sort of where we're trying to go with actually financing an asset on chain. Let's start with Tire LLC and Bitcar. So in today's world, you send an invoice to your customer. They approve it. It goes through their accounting system. They say, okay, we'll pay you in 30 days later. They might give you a payment notice at some point that they'll issue that payment. And so what we're building is this off-chain protocol. Why off-chain? For two reasons: scalability and, but also more importantly, data privacy. So those transactions, a Tire LLC invoicing a bunch of tires to their customer Bitcar, is something that's it's very private. If this information would all be on chain, it would expose too much information about their trade secrets, how they're able to produce the tires the way they do them, what their profit margins are, and so on and so forth. So for that reason, we started building out this peer-to-peer network, but we use Ethereum for a few key components. The first part is identities, right? So Tire LLC and Bitcar Inc. They both use a public key to sign messages to be discovered on this peer-to-peer network, which we use Ethereum to store and announce these public keys. So any message that is transacted off-chain is signed by an identity that is maintained on-chain. The second thing is, well, you want to make sure those off-chain transactions are immutable and time-stamped, right? We call this anchoring. So whenever a transaction is sent to your counterparty, what you do is you hash the transaction, you commit to hash on chain that will allow anyone to verify that this state existed at some point in time, at that point in time that it was committed to on Ethereum, and it can be used by other items in our product to refer to, which brings me to those non-fungible tokens. So I've mentioned that Tire LLC is sending an invoice to Bitcar, and Bitcar is saying, well, in, let's say, if they're lucky, 30, more likely 60 days, they'll get their money. Well, Tire LLC needs to pay their salaries every month. They need to buy the goods. They need to buy the chemicals, the rubber, whatever, ahead of time, right? So they have this problem that they have to produce this order, but they're only getting paid 2 months later. So what they want to do is they want to fill that gap in liquidity, in cash flow. So in today's world, they would go to a bank and say, here, I have this invoice that I've sent to Bitcar. They're paying me in 60 days. Would you be willing to lend me this money so that I can run my business and can grow? So what the talk is about doing this in DeFi, doing this with accessing liquidity from something like Maker, And so the first step to that is actually minting a non-fungible token. This non-fungible token represents a claim, a certain part of this. In the invoice example, it's an unpaid invoice NFT, which is what we call the claim by the supplier that there's money coming in from the buyer in 60 days. I've mentioned that we commit to these every transaction on chain. We commit to a hash. The way we actually do this is not just we don't take the entire document, so the invoice with the address, the line items, the tax information, all the things you would need for regulatory purposes, but we actually we create a Merkle tree out of all of this information. So each field of an invoice, for example, the amount, the buyer, the supplier, and the due date, all of these are individual leaves, which gives me this property that in a Merkle tree, I can now create a proof of just an aspect of a document. I don't have to reveal the entire document to be able to prove that the hash on chain is actually what this document is. I can give you a Merkle proof saying that the buyer of this invoice is Big Car Inc., that the amount is $15,000. And all that can be verified with this anchor, which is the Merkle tree of all of these fields. So we use this to mint NFTs. So here, what the NFT does is it just shows that there exists an off-chain document that has a certain value that is an approved invoice by the buyer for a certain amount that is due on a given date. And what you can then do is you can sell this NFT, you can transfer ownership over this NFT to another party, which would now entitle this new owner of the NFT to receive the money that the buyer has promised to pay at some point in the future. So the NFT registry needs to access this off-chain data, the information about the invoice, and we can do this with a set of Merkle proofs. So to walk through the flow, we have this off-chain invoice for which we mint this NFT that is just a subset of information, right? Just information I'm willing to reveal publicly that the financer, the bank, would need to know. So like in this example, it would be the amount, the buyer, the supplier, and the due date. And then I can take that, I can give it to a traditional finance like product, or I could use something like our Tin Lake to then access liquidity on Maker, Compound, whatnot. But there's still this problem with this whole setup. It's that to be able to price an asset, to be able to know that this is actually a valid invoice, this is how reputable the buyer is, how likely you're getting paid, right? Because as someone financing this invoice, I want to make my interest rate depend on the reputation of the buyer and the supplier. So you have this problem, though, that now I'm still making all of this information available on chain, right? The amount and the buyer. And so for that, we're going to use snarks. Instead of having to reveal this publicly when you mint an NFT, when you sort of create this, tokenize this asset, we can now mint an NFT that just submits a proof about certain things instead of revealing all of the data. In this example, what we want to do is we just want to give the asset a value instead of like the full invoice amount. So for example, if you only seek funding for $10,000 instead of $15,000, you could mint this NFT to be a claim on $10,000. But of course, we need to make sure that the value of the invoice amount is more than that. And we say we're not going to reveal who the buyer is. We're just going to give a credit score. But of course, you need to be able to trust the score. So as a supplier who mints this NFT, I need to prove that I actually have that my buyer has this credit score of 97, and the funder, the bank, whoever, needs to be able to verify that. So this is where we'll start using snarks. I've mentioned this a few times without giving a lot of background. I'll try to explain it in one slide. Of course, it's taken me many months to get into this topic, and this one slide doesn't do it justice. But there's a lot of information online, so go follow that. But basically, a zero knowledge proof is it's a proof that allows you to demonstrate things without giving away any information. In our example, we want to demonstrate that the NFT amount is less than the invoice amount without revealing what the invoice amount is. We also want to demonstrate that there's a credit rating without saying who the buyer is that has this credit rating. So snarks are very easy to verify, extremely hard, computationally infeasible to fake. So you can basically prove almost arbitrary computation, and so this does support features like signature schemes, so you can verify a signature inside of a snark, and you can use hash functions, which comes in handy when we want to verify these Merkle proofs that I talked about, with how we encode our off-chain data into this into the structure where each leaf in the tree is a field, and you want to reveal or you want to prove certain fields are part of this anchor on chain. So we've done the second part I want to talk about is give a brief introduction to Socrates. Socrates is a Python-inspired domain-specific language for actually defining these zero-knowledge proofs. There's a very simple example here. You have A and B, and you have these inputs A and B, and you compute that the result is A plus B. And writing this piece of code will give you a snark that you can then where you can create a proof for, and you can verify that this computation was actually correct. It offers the primitives that we need to efficiently prove things in snarks. So I mentioned hash functions and signature schemes. So this takes a huge load off your plate. What we actually did in this proof of concept in this example with rating revealing the credit rating of the buyer but not the actual buyer is we created this snark that takes a list of buyers, and so public keys of buyers and their rating as public inputs. So anyone can see Coca-Cola has a score of 90 and Volkswagen has a score of 85 and who knows what. And then anyone can take this list, can take their invoice and prove that any one of these buyers that are in this list of credit ratings actually signed this asset, so was privy to this off-chain transaction, and then reveal that the score is a given without revealing who it actually was. We also do things like making sure that the invoice amount is actually higher than the NFT amount, right? So we have these are the public inputs, and the private inputs are up top. So using Socrates, this was actually maybe at the top of my head 100 lines of domain-specific code that we had to write that allows us to do this computation. Does this EDDSA signature verification, Peterson hashes, and so on, to then very easily build this snark and let us prove it and integrate it into our NFT registry. So I've mentioned Socrates a few times. I've mentioned cryptographic primitives. So I'll hand over to Stefan from the Socrates project, who's been working on implementing the baby jub cryptographic primitives in Python and including that into Socrates, which is really what made all of the stuff that I've been talking about computationally feasible. So I'll hand over to you.
Thank you. Can you hear me? Awesome. So I'm Stefan. I'm a contributor to Socrates, and I want to give you a very, very high-level introduction into the math, and especially why we need a new signature scheme and a new elliptic curve and can't use the existing primitives we have, for example, from Ethereum, the well-known ZEC-P curve. But first, some background on Snark programming. That's the function or the program that Lucas already mentioned or showed before. And I added this one detail. That's the mod P you see here. So as the types you see already of the function signature, whenever we work in zero, like in Snarks, we always work with feed elements, right? And that means, for you to know, is that feed elements in the end, that every computation we do with these elements, in the end, they will be computed with mod P, right? Which is just as their feed elements, they are in a finite field. And so like this is a really important takeaway, that whatever computation we define in a Snark, it's wrapping around this field, right? It's wrapping around this P, which is a very important fact to know, right? And if you know, ask yourself, where is this P coming from? The P is actually defined by the curve of the proof system, and we will cover this later a bit as well. And now, why do we need an elliptic curve in a Snark? Lucas already gave some hints here. So first of all, it's to enable digital signatures. They're an important primitive for all kind of stuff. In particular, obviously, to verify them in zero knowledge and add some kind of notion of identity to these proofs. And they're based on elliptic curves. And the second big application is efficient hashing. So all the bit twiddling hashes we know, like SHA-256, are very inefficient in Snarks, and there are more efficient replacements we know that are based on elliptic curves as well. Speaking about elliptic curves, so what is it? I will not give a detailed discussion here or definition here. For the sake of this talk, an elliptic curve is really just a group of points of finite size, like fixed size. You see now this image here, which is like 4 points in total. That's kind of also the order of this group, right? So then we talk about, hey, we have 4 points. And these points have coordinates, which are also represented in a finite field. And the important thing to know is that this group is closed under addition. So you see that I can take the point P, add it to itself, I get 2P. I added another P to it, I get 3P, and at some point I will get to infinity. And I will also loop around this group of the elliptic curve. And by addition, right? And addition is actually more or less all we do in elliptic curve cryptography. It's the mathematical operation that's underlying all the signature schemes and also asymmetric encryption protocols. And luckily we have a closed formula for this. It's here. You don't need to know any details about it. Obviously there are 2 coordinates, right? Because we talk about points. But the really important thing to realize is that there's also a mod P behind it, right? Because obviously in elliptic curves, we also work on finite fields. And if we now would implement this in a Snark, we would have to implement this mod P operation, right? In Socrates or whatever like programming language you're using to define the Snark. And this is very costly, right? So you can imagine mod P is doing comparisons and all kind of things. And due to this, there was a clever trick discovered, I guess, from the Zcash people. Maybe you guys realized it already as well. So we have talked about this mod P here, right? So kind of all the computation we do get wrapped around this P. So let's just get this for free, right? And basically define a curve where this mod P operation on the very end is exactly the size we anyways wrap around in our proof system. And this is exactly what, in the end, embedded curves is all about, right? So it's basically having a kind of host curve that's defined from the proof system, and then fitting another curve inside that exactly matches the field size. And for the BN1 to 8 curve, just for you to know, this is the curve we have pre-computes in Ethereum for. This curve is baby jub, and that's why we use baby jub for all of the operations Lucas mentioned. And maybe a last thing to show, you can have a look at the code. It's all written in Socrates DSL. That's the same formula as shown before, just written in the DSL language. That's how the curve is implemented. And for people that are got really interested, there's a very in-depth article on constructing this curve, and also about the entire project that we now discussed about on these Medium posts, and there are the repos. So feel free to check it out and use it and comment.
I'll tweet about this as well. So if you want to find the links, just look for it in a few minutes on Twitter. Great. Thank you very much.
Thanks. Thank you so much.
Probably over time, but come find me for questions.
No questions. Good.
Yeah.
If you have a question, go ahead.
I can ask. All right. So going back to the fitness of primitives to use in snarks. What's your opinion on the MIMC stuff, like MIMC hashes and MIMC ciphers? Like, are there? Can you consider them secure enough to use? Are there any pitfalls that you know? So.
Yeah, that's a good question. Sorry. Yeah, that's a good question. I think the community is still figuring this out. I mean, I'm not sure if MIMC is still like the hash function that's mostly poked right now. So there's already like new versions of it called Poseidon, which is even more.
I meant that. Yeah.
Okay, which is even more efficient. And that's being constructed by experts in the field, and now goes through thorough like cryptanalysis, and time will tell. But for now it looks really good, and I think we will see first projects using it.